So my previous recording was messed up. Um, so I've already gotten everything written. You're not gonna see me live calculate anything unless I spot something. All right. So for number one, we know that the angle is supposed to be in the second quadrant, and tangent of the angle should be -6. When you draw what that angle looks like, you'll have this show up, right? It's just going to be some angle that lives in the second quadrant, and then you want to get tangent to be -6. Well, the way we break that apart, tangent is opposite over adjacent, and we want to have those values give you back -6. Opposite over adjacent, so we would split this up into 6 over 1, and then we put the negative in the right location. For this quadrant, you want the x value to be negative because the x value is negative, right? You see x comma y here. So the x value is negative, the y value is positive, following the direction of my cursor. And then to be able to read off the values of sine and cosine, well, we need the hypotenuse. We need the length of the hypotenuse. So we do Pythagorean theorem. We calculate 6 squared plus -1 squared plus, well, is equal to the hypotenuse squared. So then you do that calculation, and then you will get h is the square root of 37. Okay, so then that's how we end up getting this label. And then lastly, we read the values off of theta. So, or off of the triangle, using this angle mark as our perspective. So that tells us this is opposite, that is adjacent, that's hypotenuse. We knew that was hypotenuse. But opposite over hypotenuse gives you sine, and then adjacent over hypotenuse gives you cosine. Okay, maybe I can use the hand. Let me see. Yeah, that should be good. All right, great. Right. For number two, so there's two ways you can think about this. There's um, the way that both me and Nagi find to be more natural, which is thinking about the distance between 2 points, maybe because of mathematical training. And then there's the approach that students have told me about, which is that you can take those 2 points that are given and insert them into the equation of a circle. Uh, the additional square root here is actually just because I sort of went on a bit of a tangent and I explained that actually if you just take the equation of a circle, general equation of a circle, x minus h quantity squared plus y minus k quantity squared equals r squared, you take the square root of both sides, you wind up with distance formula. You get distance between the points x comma y and h comma k is r. That's what you get. So, in fact, the two approaches are equivalent, which is kind of cute, I guess. All right. Something's going on with my computer. Hopefully, nothing too bad. Okay. Yeah. So, but then I proceed by using the way that it seems you students are more familiar with, which is plugging things in. So you plug the x coordinates. This would be x comma y. This is a point that lies on the circle, which we denote x comma y. This is the point of the center, uh, which corresponds to the point h comma k, or the variables h comma k. So then you insert into the formula, and then I guess the only notable thing is that this k, because k is negative here, it's going to flip the sign from minus to plus. Okay, so we did that. We plugged the values in, and then you just compute. So -4 quantity squared plus 5 squared equals r squared. Calculate, calculate. R squared equals 41. And, well, you don't need to take the square root because you're going to then plug back into the general formula of a circle using the center, h comma k, 3 comma -2. So giving you the -3 plus 2 there, and then r squared right there. So that is the equation of a circle centered at this point, passing through that other point. All right. Number 3. Right. So, I can't really imagine anyone using Nagi's approach, but I guess if you do that, you hopefully know what you're doing. Um, the a standard approach from whenever you learn algebra, which is probably in high school, is that you solve for y. So we take this guy, we solve for y so that we end up writing the equation in slope-intercept form, and then we read off the slope from slope-intercept form, right? So we had to solve for y first. Well, the first thing that I do is up here, going from uh, what's printed to this, and I subtracted -8 from both sides, right? So that's going to give me this. Then the next thing I'm doing is I'm dividing by -5 to get to this. So notice the dividing by -5, we just get y on the left-hand side. The negatives will cancel when we divide, so we get 8/5, and then 40 divided by -5 gives me -8. So this is this equation of a line rewritten in slope-intercept form. We read off the value for the slope, m, 8/5. And then to answer these two problems, well, we know what point the lines should pass through, and we just need the slopes, and then we can use point-slope form. And I'm reminding you what point-slope form is here. It's this format of a line, y minus y naught equals m times the quantity x minus x naught. And what this says, or these two things, uh, the values x naught and y naught specify a point that this line will pass through, and then the m specifies what the slope of this line should be. So these two things will specify uh, a given line, and then what we do is we just plug things in. So we know what the slope for a line parallel to the given line should be. It should have exactly the same slope, 8/5. And then the point that we want the line to pass through is 4, -1. Well, we plug that right into point slope form. We would get the +1 from uh, uh, double negatives. Negative, -1 becomes +1, and then we get that right by just simply inserting. Now, to go from a line parallel to a line perpendicular, well, you need to know that the perpendicular line will have a slope that is the negative reciprocal of the line you started with. That's how you compare between a line and some line that is perpendicular to that given line. So we just flip this fraction and negate it. So you end up with -5/8. And then the x naught, y naught stay the same. So yeah, those are the two values. For number 4, this is the vector calculation problem. So the vector w, we just copy this definition down, but then we insert what u and v are supposed to be. So that's what I've done here. And then I multiply in, just I sort of break the computation into steps, but like really you could kind of put everything in one set of brackets with two equations. But yeah, let's just talk about this way. So multiply the 3 in, so you get -6 on top, you get 15 bottom. For this one, I'm multiplying the 2. Notice I'm leaving the negative here. You could actually just multiply both values by -2, but then you have a plus in between. For whatever reason, I just prefer thinking of it like this. So multiply the 2, then you get 12 and -2 here. And then we subtract across. -6 minus 12, -18. 15 minus -2. 15 plus 2 is 17. So this ends up being the vector you get after doing your arithmetic. Then to get the magnitude of this vector, this is distance formula. So you take the square root of the components squared and then add it together. So we square the -18, we square the 17, we add the two resulting values, use a calculator for that, and then you take the square root. That gives you this. And then you should tack on miles since it says something about what the units should be. And of course, exact values, but this is kind of a thing you would anticipate. Why would you round this is a completely valid number. Yeah. Okay. For number 5, verify this identity. So this is kind of what I would expect a student to do. There are different approaches you can take for verifying identities. You can do all kinds of different algebraic steps, so long as you end up getting that left-hand side equals right-hand side, right? But the principle is that you do things to simplify the left-hand side, you do things to simplify the right-hand side, and then these two things should match. If they don't match, you've probably messed up somewhere. And the reason, I mean, mm, the reason I think that this is the more standard way of doing it is because for me, like, I look at cosecant and I don't like cosecant. Right, sine and cosine I'm happy with, but cosecant is kind of just an oddball. You know, secant is also kind of an oddball. And tangent is okay, but cotangent is also weird. Like sine, cosine, and tangent, those are the main guys. If you see secant, cosecant, cotangent, you kind of want to just reciprocate those things. So here we see like that's what I'm doing with my first line basically. Although I am treating these two sides separately. It's just this is like what I immediately register as the first step that I should take. All right. Then notice that with the right hand side, the only thing we can do is just multiply this to get rid of the fact that these are two separate entities. Instead, we just think of it as one fraction. Cosine squared over sine. Okay. Um, left hand side now. After rewriting this, well, you would have 1 over sine of t minus sine of t. And then the only thing you can do is just try to combine these guys. Right, so then we view this guy as a fraction, and then we recall how do we subtract fractions? Well, we need a common denominator. So we obtain that common denominator by multiplying top and bottom of this by sine. So multiplying the top by sine, we end up with sine squared. And then bottom, we get just sine. So now we end up with a common denominator. And then how do we subtract fractions now? We subtract the numerators across. Denominator stays as the common denominator. So we end up with 1 minus sine squared t all over sine t. And then when you see this 1 minus sine squared t with and then I guess cosine, like it should make you think of the Pythagorean identity. So you start out with this guy. This is what you would commonly have memorized if you didn't have a formula sheet, and then you would subtract the sine squared to the other side to get this numerator to show up. And so this step is applying the Pythagorean identity, and then, hey, look, left side equals right side. Very good. We've verified the identity. Okay. Number 6. So we have this angle. This angle is inconvenient. It's outside of our usual, it's outside of 360 degrees. So we want to like reduce the angle. And the way we do that is we get rid of multiple wraparounds of the unit circle. In this case, we want to add copies of 360 degrees to reduce the angle. And it turns out that we could add 2 copies and arrive at negative 30 degrees, or we could add 3 copies and arrive at 330 degrees. I would stop at the negative 30 degrees just because at this point I know what a 30-degree angle looks like. The fact that it's negative just means it's going in the opposite orientation, which is counterclockwise, shown in this diagram. Right? If you add another copy of 360, you end up getting this 330. For me, like I have to think about what that means. Like I'm gonna end up doing 360 minus 330 to get 30 degrees, and then realize, oh, okay, it's 30 that's negative. Like, this guy is outside of my intuition, but it is this large angle. All right. Right. So then we have to construct this diagram. I mean, first we would just have this point. Like we would just draw this point. We would draw like a 30-degree thing, and then I went through a few different approaches that you could take with this problem. So one way is if you know how to label the sides of a 30, 60, 90 degree triangle, or yeah, 30, 60, 90 degree triangle. Um, 1 is opposite the smallest angle, 2 is opposite the largest angle, which is the 90-degree angle, and then root 3 is the remaining guy, or yeah, it's the larger leg of this right triangle. Right, so 1, root 3, and 2 are is how you would label it. And then, well, when you have this, you could just read the values off. Um, I guess just for consistency with how I've been doing things in recitation, this guy I would think of negatively because I noticed that this is in the negative y. The y value is negative, so you could label this side negatively, and then just read the values off. Or wait, yeah, that will give you the correct values. Um, another approach would be um, dealing with the reference angle. So this is using the principle that, like, I mean, this is, I guess, if I want to tie this into this first approach, it's a way to not have negative distances, which maybe make, because negative distances is kind of like uncomfortable, right? You know distances shouldn't be negative. Something weird is going on, I guess. And one student pointed this out in recitation. And I didn't really have a good answer for that, but I thought about it and I've kind of figured out like what's going on. Um, I don't have that connection written here, but uh, so instead of using this negative thing, like instead we could think about say the reference angle 30 degrees. So if we then so what do we know about the trig functions evaluated on the reference angle versus on the actual angle, right? 30 degrees versus negative 30 degrees. Well, we know that they're going to be the same value up to plus or minus, right? They could be off by a sign. And so if you have unit circle memorized, at least for the first quadrant, you can write down the values. You would get half for this, root 3 over 2 for this, root 3 over 3 for this, or 1 over root 3 as I like to write it. And then you reciprocate to get the other side, and then you figure out what the signs are. And then the consideration for the signs, well, you think this is in the fourth quadrant. So that means that cosine is going to be negative. Cosine is the x, or wait, not cosine, sorry. Sine is going to be negative because the sine is the y coordinate, and the y coordinate is negative in the fourth quadrant, whereas the x coordinate is positive. So we know sine and its reciprocal, cosecant, will be negative. Then, of course, tangent and cotangent will be negative because to get tangent, you divide sine with cosine. Negative divided by positive is going to be negative. Similarly with this cotangent, or just by reciprocation. Okay, so that's like another approach. And then I think another common approach that students will have done is to just have the unit circle. So have, uh, I did have a copy open. Okay, uh, that's going to be interesting. Yeah, well, anyway, if you looked at the unit circle, you will have gotten this coordinate. And then the idea is that x comma y corresponds to sine or cosine comma sine. So this immediately tells you what the value for cosine of theta should be, root 3 over 2, and what the value of the sine of theta should be, negative a half. And then to get tangent, you would divide the two, which you have to do correctly. You get 1 over root 3, or if you rationalize the denominator, you get root 3 over 3. And then you just flip the fractions to figure out the rest. Nothing more to say about that. Number 7. So, right. There's two ways, two main ways to think about this. So first I'll talk about this just using the formulas. Okay, assuming you have a formula sheet and you have the formula somewhere, then what you can do is look up what pi minus alpha does as a transformation, and you'll get like these two equations. You'll get that sine of pi minus alpha is equal to sine of alpha, and cosine of pi minus alpha will be negative cosine of alpha. So that means that the sine function will have the same value, so it'll have negative 15 or negative 5 over 13, and then cosine will have the negated value. So we negate negative 12 over 13. That's two negatives make a positive, so we get 12 over 13. So that's one way to do it. What if we didn't have this formula sheet, but we knew things about transformations? So we would then view this pi minus alpha, and we would recognize that it's actually a horizontal. I would call this a horizontal reflection. It's doing this kind of thing. It's swapping the quadrants 1 and 2, and it's swapping quadrants 3 and 4. Then when you, if you then can visualize this, then what you know is it's gonna leave the y coordinate the same, but it's gonna flip the sign of the x coordinate, and the x coordinate corresponds to cosine. Cosine is the x coordinate, so cosine gets flipped. That's why we go from negative to positive, but the sign does not get flipped, so it stays negative. Okay, so that's another approach. And then the third approach would be to do this kind of stuff. Right, so the way that what this is, blue is uh, the point that you would get for the angle alpha. Okay, so you could then label the triangle just by breaking things apart. 13 is going to be so alpha will be, it's going to be hard for me to point to things, isn't it? I guess I can zoom in. So alpha, oh no. I hope my recording's not going to get messed up. Okay, yeah, so alpha is going to be this little guy that I don't have drawn, but it's trying to motion towards it. So then what you do for sine to break it apart, sine is opposite over hypotenuse, opposite side is 5, hypotenuse is 13. Then you recognize that 5 should be negative because the hypotenuse is never going to be negative with this approach that we take with pretending we can have negative distances. Cosine is adjacent over hypotenuse, so it's going to be adjacent. We would have 12 over 13, and then we recognize that this guy has to be negative, and everything checks out because this is negative in the sense that the y coordinate is negative. This is negative in the sense that the x coordinate for this point is negative, right? So all these lengths check out. That's good. Just kind of sanity checking our work so far. And then, next we have to think about what does this transformation do to beta. Now, if we already knew this, then we would just be able to immediately say, well, it's got to go to this point in green. And then we could do the labeling of the sides. We would get negative 5 here, 12 here, 13 there. If we didn't know this is what this transformation is doing, then the way that I've done this in recitation is I've broken this into steps. So you can view this as two transformations done one after the other. The first transformation is alpha goes to negative alpha. You're negating this angle. And then the second transformation is you take that angle, negative alpha at this point, and then you add pi to it. Right? Adding pi is just rotating by half of a full revolution. Negating the angle is just going the same angular distance, in quotes, except in the opposite direction. So instead of counterclockwise, you end up going clockwise. So that's what happens with red. Red is this intermediate step. You instead of going alpha to get to the alpha, you go negative alpha, and then that gives you this point in red. You see, right? Instead of this way, you go the other way, but the same amount of angle, just in the negative direction. And then finally, you would add pi to that, which brings you right around to here. So you end up knowing that you land in the fourth quadrant, and then you know, well, this transformation keeps the reference angle the same. Like, it's going to give you the same reference angle. The triangle is pretty much the same. The lengths of the sides are the same. Just the signs are different because you have shifted yourself into a different quadrant. And then you could fill in the sides, and then you could just figure out those values. But I mean, I think it's pretty clear. Like, thinking about these things as transformations is actually the faster approach. It's just that for me, it took a while to actually notice like what's happening, and so I didn't emphasize this in recitation simply because I didn't. It took me a little bit to dawn on me like what was actually going on. Now I understand better. All right. Part B is well, okay. So saying that we have this, like whatever the work that you did was, if you had the sketch of where beta lands, then you would be able to see like visually just see that it's the fourth quadrant. If you didn't have any of that, if you just had like this, somehow you just algebraically, whatever method you took, you algebraically computed these values, how would you then recognize that should be in the fourth quadrant? Well, it's about which values are positive and which values are negative. And a little bit of a trick I've used is to just draw a coordinate plane, label the axes cosine and sine because cosine is x and sine is y, and then we see that cosine is positive, sine is negative. Okay, well, cosine is positive, sine is negative. We've landed in the fourth quadrant. There we go. Done. All right. And then number 8. Uh, number 8. So with this one, we have a point 20 comma negative 21. So we draw that point. Oh, and then we want to compute all 6 trig functions for this angle theta. Okay, so what have I done here? So you would start by plotting this point, drawing the hypotenuse, and then you would probably sketch what the reference triangle is. And then what I've done below is shown what the reference triangles should look like for all 4 quadrants. This is because I saw some people draw this triangle incorrectly. So this is the correct triangle, and then this would be the angle, and so then you can read off the values after you label the sides of this triangle. If you don't draw this triangle correctly, I saw people, I'll just show you, like, I saw people label this as the triangle, and then what happens is that you have flipped the adjacent side and the opposite side, so then all your values are incorrect in some fashion. Yeah, so that's not great. Okay, so yeah, draw your reference triangle correctly. That's important. Um, and then we have what? So 20 minus 20 minus 21, and then you see that this is of length 20. This is quote unquote length negative 21, and then this is 29. How do you get 29? Using Pythagorean theorem, you square 20, square negative 21, add them, put it in the square root. That gives you the hypotenuse length. Which, of course, we would plug that into a calculator. And this guy is because, well, when you do this calculation, you would get 841, and then I did not recognize that this is a perfect square. It doesn't look like a perfect square to me. I don't know, just looks a little bit funny. But yeah, turns out you take a square root of that, you get an integer. So this is actually a perfect square. That's good. So we can actually just call that 29. And then we read off all the values, right? So sine opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent, and then to get the other column, cosecant, secant, cotangent, just reciprocate across. And then the signs will be correct because we have allowed us this mental shortcut of having possibly negative side lengths. And then what I've done in blue here is I've tried to kind of explain why Nagi's approach is pretty much the same as this, just avoiding avoiding using negative side lengths. Like it's the same thing, uh, but just slightly different. Like if you think about what the formulas are doing, uh, you see that as the same, right? It's just like for a general triangle, cosine is the x coordinate, sine is the y coordinate, hypotenuse would be r, and then you just you follow things the same way. Like sine is opposite over. Wait, hmm, I can explain that a little bit better. Where's my cursor? Guess let me for angle theta, this would be r. This is x comma y. This is the value y. This is the value x. Yeah, there we go. Yeah, exactly. It's this. So then, like, how do you read off sine? Opposite over hypotenuse. How do you read off cosine? Adjacent over hypotenuse. See that I'm getting the same fractions. And then how do you read off tangent? Opposite over adjacent. There we go. We've reconstructed his formulas, Nagi's formulas. So then, like, yeah, okay, x is actually 20, y is 21, reading off of or decomposing this coordinate, and then you calculate r, which we did over here. So yeah, these two approaches are equivalent. All is nice and good. All right, and well, that's the last problem. Great. So I guess that's it. Um, anything else I want to say? Well, hopefully you could follow this these explanations of these problems. If you have further questions about about this, like feel free to email me with the question. Um, I probably won't be able to have that much time to go through things during the next recitation because we're gonna have to cover the next homework uh, on graphing sinusoidal functions. Maybe we'd have 10 minutes to talk about questions that you might have. Uh, yeah. So if you have further questions, like we might be able to spend 10-15 minutes on it during the next recitation, but otherwise, like, do email me. That's the best way to ensure that I actually see your question. All right.